Many questions have been raised about magnetic pole reversal and the end of the planet. Is it really that concerning in 2025? Let me remind you of the science lessons we had in middle school when we learned about magnetic fields. A magnetic field refers to the area surrounding any magnet where its force can influence materials that are susceptible to magnetism. Do you remember the experiment where we sprinkled iron filings on a table with a magnet beneath it, or on a piece of paper containing a current-carrying wire? What happened then? The iron filings would scatter into specific patterns extending from the magnet's two poles, which are called the magnetic poles. These patterns form within a defined space around the magnet or the wire. This space is what we refer to as the magnetic field. Of course, the size of this field depends on the magnet size or the strength of the electric current passing through the wire. Magnetic materials naturally exist in the environment, and humanity has been aware of them since ancient times. Prehistoric humans noticed that certain rocks influenced specific tools made of materials like iron. Over time, as they learned about other materials, they discovered that elements such as cobalt, nickel, and chromium also respond to magnets. As our understanding of nature evolved, we came to realize that magnetic fields emanate from the poles in opposite directions. Imagine a magnet shaped like a typical remote control battery. The top pole emits the magnetic field downward, while the bottom pole emits it upward, forming circular loops. Now that we've covered the scientific basics, let's move on to the geological fundamentals. Let's take a closer look at our beloved planet, which is made up of 4 layers. For now, we'll focus on the first 2, but I'll briefly mention all 4 for context. 1. The crust. This is the outermost layer, the one we live on. 2. The mantle, found beneath the crust. This layer accounts for about 84% of Earth's total volume and is approximately 3,000 kilometers thick. 3. The core. This is further divided into 2 main layers, which are the most important for our discussion. Let me explain these separately to make it easier to follow. The outer core. The outer core is a liquid layer about 2,300 kilometers thick, extending to a depth of around 5,150 kilometers, where it meets the inner core. It is primarily composed of iron and nickel, with temperatures reaching approximately 4,000 degrees Celsius. The deeper you go, the higher the temperature rises. This increase in temperature causes the iron and nickel to become more fluid and less viscous. Due to these varying temperatures, thermal energy is constantly being transferred throughout this layer in a random and chaotic manner. The inner core. The inner core is the deepest point of our planet. It is a solid or semi-solid sphere compressed by gravity to a radius of about 1,220 kilometers, which is roughly 20% of Earth's total radius, or 70% of the Moon's radius, in case someone like Tariq Alam asks you. All the information we have about the inner core is based on estimations and interpretations of seismic wave data, as we currently lack the technology to physically reach it. However, it's widely believed that this core is also composed of iron and nickel, along with small amounts of other elements, and its temperature is close to that of the Sun's surface, approximately 5,400 degrees Celsius. I know this might sound a bit complicated, but I'm trying to simplify it as much as possible, so stay with me. Now, imagine the solid inner core radiating heat at nearly the same temperature as the Sun's surface. Where does this heat go? It rises to the outer liquid core above it, which is constantly moving, losing heat, gaining heat, and transferring it randomly and continuously. Does this remind you of something? Yes, like ocean waves. However, the difference here is that this liquid isn't water like the ocean, but primarily molten iron and nickel. Remember, we talked earlier about these elements being naturally magnetic. So, what does this mean? It means you have naturally magnetic materials receiving energy from the intense heat below. This energy causes them to generate a magnetic field around them, similar to what we discussed earlier in science lessons. Now, imagine replacing the iron filings in the school experiment with molten iron and nickel, and instead of the electric current, you use thermal energy from the inner core. This makes the entire outer core function as a giant magnet that creates a magnetic field affecting certain materials depending on their properties. I hope things are a bit clearer now, right? Let's continue. Remember when I said the area influenced by a magnet depends on its size and the energy used in the experiment? This is evident here. Imagine the massive size of the outer core and the furnace-like temperatures. How strong would such a magnet be? And how far would its influence extend? Let me tell you, this massive magnetic field extends from the Earth's core and stretches into space in all directions, forming an oval shape. It reaches about 90,000 kilometers toward the Sun and extends about 6.3 million kilometers in a tail-like shape away from the Earth. This magnetic field created by the Earth's magnet is what we call the magnetosphere. Before you wonder why it's not perfectly symmetrical and looks dented on the side facing the Sun and stretched out on the opposite side, let me explain. Without the magnetosphere, life on Earth wouldn't exist. It acts as a protective shield, deflecting harmful solar radiation from reaching our planet. This dent, known as the bow shock, occurs because the powerful solar winds push against it. The immense pressure from these solar winds causes the magnetosphere to compress on the sun-facing side while stretching into a tail that extends millions of kilometers behind Earth. Interestingly, the small portion of solar radiation that penetrates this shield is what creates the auroras we see in northern regions. Now you have the basic knowledge to understand the core concept. Let's break down what's happening, step by step, without exaggeration or misinformation. The Earth's magnetic field, like the magnets we used in school, has two poles, a north magnetic pole and a south magnetic pole. These are not the same as the geographic north and south poles you see on maps. In fact, their locations don't necessarily align, even if they occasionally overlap by coincidence. What does this mean? Are the magnetic poles fixed in place? The geographic poles, yes, are always fixed. We won't wake up one day to find Antarctica next to China. However, the magnetic poles are not fixed. Why? Because they are not physical locations. They are determined by the position of the Earth's magnetic field, which is tied to the motion of the liquid outer core. If the source of the magnetic field shifts, the poles move as well. Imagine drawing an arrow on a piece of paper pointing to a wall in your house. If the paper is on a stable table, the arrow's direction won't change. But if you place the paper on water, and the water moves, the paper will shift, and the arrow will no longer point at the same wall. The wall represents the geographic North Pole, and the arrow is the magnetic North Pole. This distinction is important to avoid confusion. Historically, scientists once believed that Earth's magnetic poles were fixed. Why would they move? But in the early 20th century, geologists, including the famous French scientist Bernard Bruns, noticed something unusual. Certain volcanic rocks from ancient periods were naturally magnetized, but their magnetic poles were reversed compared to Earth's current magnetic field. This was a critical observation. By the late 1920s, the Japanese geologist Motonori Machiyama discovered that these reversed magnetic poles in rocks dated back to periods before or during the Pleistocene epoch, the Ice Age, which ended about 11,700 years ago. I won't delve too deeply into the scientific details, but over subsequent decades, as we studied the Earth's magnetosphere and geology more closely, we developed more precise measurement methods. This allowed us to map the timeline of how Earth's magnetic poles have reversed due to the chaotic movement of the liquid outer core. By examining ancient volcanic rocks both on land and at the ocean floor, scientists were able to determine the orientation of the magnetic poles at various points in Earth's history. What did we learn from all this? We learned that Earth's magnetic poles reverse periodically, though not on a fixed schedule. This happens due to the flipping of the magnetic field generated in the outer core, as explained earlier. Earth has reversed its magnetic poles about 183 times over the past 83 million years. The last temporary full reversal occurred approximately 42,000 years ago during what's known as the Lost Champs event. This reversal lasted around 1,000 years. The last permanent reversal, known as the Bruns-Machiyama reversal, occurred about 780,000 years ago. Now you also know the origin of these names and the approximate timeline of these events. Studies have varied in estimating the duration of a magnetic pole reversal, ranging from less than 100 years to up to 22,000 years, according to a 2019 study. Additionally, We now know that the time Earth takes to reverse its poles isn't fixed but generally falls within a range of 2,000 to 12,000 years. Currently, we are experiencing a slow and gradual magnetic pole shift, occurring at a minimal rate each year. Does this mean it could happen overnight? No, the process could extend into the lifetimes of your great-great-great-great-great-grandchildren, if not longer. Let me reassure you further. Based on measurements taken since the mid-17th century and confirmed by 2014, we are indeed in a period of weakening of the Earth's magnetic field. This weakening is increasing by about 5% per decade, meaning that every 30 years, the field loses a maximum of 5% of its strength. However, even with this decline, the magnetic field is still stronger now than it has been at any point in the last 50,000 years. At this rate, it could take another 600 years or so before a full reversal might occur. Will a magnetic pole reversal end life on Earth? This is likely the main question for most people, and there's no definitive answer from any schoolbook, as we're dealing with phenomena that no one alive today has experienced. However, based on the data we have, a magnetic pole reversal would result in a weakened magnetosphere. This, in turn, would mean more harmful solar radiation reaching the Earth's surface. What does that imply? It could lead to health problems, such as skin diseases and cancer, as well as technological issues in a world heavily reliant on satellites, affecting GPS systems, communications, and even social media. Additionally, compasses would no longer point accurately, and birds, fish, and insects that rely on Earth's magnetic field for navigation would struggle as well. But are earthquakes and volcanic activity linked to magnetic pole reversals, as some claim? The answer is no. Don't believe anyone making such claims without solid scientific evidence, which currently does not exist. To date, there's no proof that the Earth's magnetic field affects tectonic activity, as earthquakes and volcanoes are primarily caused by the movement of tectonic plates, which are unrelated to the Earth's core responsible for the magnetic field. In fact, the reverse is more likely. Earthquakes and volcanic eruptions can sometimes cause localized changes in the magnetic field, not the other way around. So, why do some people claim this is the cause of our problems and that the world is ending? No one can predict the exact timing of the end of the world, as this lies within the realm of the unknown. While it will eventually happen, is a magnetic pole reversal the cause? The answer is no. First, the process takes hundreds to thousands of years. Second, fossil and archaeological evidence shows that previous reversals did not cause significant changes to the planet. Have there been catastrophic periods in Earth's history? Yes. But does that mean every reversal leads to disaster? No, not necessarily. Probability theory supports this conclusion. By the time this process completes, humanity may have advanced technologically to the point where we can protect people from the harmful radiation until the poles stabilize again and we adapt to the new normal. So, why stress yourself unnecessarily now? The shift simply refers to the gradual movement of the magnetic poles during the reversal process, which we've explained. As for its connection to global warming, it's not a direct one. However, a weakened magnetic field allows more harmful solar radiation, which could contribute to a slight temperature increase. That said, humans are already exacerbating global warming through greenhouse gas emissions, factory heat, and pollution, which are causing ice to melt, sea levels to rise, and other problems. You now have a general understanding of the topic. Of course, there's much more detail, but for now, you're informed enough not to panic. Continue reading and researching to delve deeper into the subject. Remember, for example, how we were once terrified of the ozone hole. As we grew older and learned more, we discovered that it's no longer the threat it once was. Everything depends on how you interpret information and the sources you rely on. Not all sources are neutral or well-intentioned, so always keep that in mind. I hope I've managed to simplify and reassure you, even partially. If you found this helpful and enjoyable, share it with your friends and let them know there's no reason for undue concern or anxiety at the moment.